Good morning, students. Today we will discuss a new topic which is correlate with my previous video presentation on diode, PN junction diode. Here we will discuss the transformation of direct current, that is DC, from alternating current using the different combination of PN junction diode. After that we will discuss the design a power supply, which we have seen in the common appliances, that is from AC to DC we are using, from unregulated to regulated, right? So here, what is the diode? I just want to rephrase your knowledge that diode is nothing but a one wave bulb. Like our heart, there is the system, the circulation of the blood from one end to the other end, but it can't go in the reverse direction. So in the diode, the same mechanisms we are following, we are seeing. And here the first we will discuss about the half-wave rectification using the diode. So we know that the alternating current consists of a sinusoidal wave, and there is the crest and trough, that means positive half cycle and the negative half cycle. So this is called the positive half cycle and this part is the negative half cycle. So using the transformer, we first use the transformer which will basically give in the output that is in the AC but alternating current, but the step down, that means the voltage will change. Means if we use the step down transformer, then the voltage will decrease, the output voltage will decrease. If we will use the step up transformer, then the voltage will increase, right? So here this is the output that is across the load resistance we can measure. Then we can get through the oscilloscope, we can see that the output will be like this. So ultimately the negative half cycle is basically missing. So because the negative half cycle missing, because there is no current flow because you know that you have to complete the circuit. When the negative half cycle, this diode acts as a negative, that means the reverse mode. So there is no current will conduct. So ultimately the circuit is open, right? So now here the same circuit is given, only there is another point which is very important that we will use, that is called the VP. VP is the peak voltage, right? The peak voltage means the magnitude of the wave. This is the peak voltage, right? So the peak voltage is equal to VP in, and here we are using, generally we are using the silicon as a material for the PN junction diode. So for this the cut-in voltage is 0.7 volt. Okay, so next, what is the V average? V average is the voltage across the diode, which we will get generally the mean. That means this is, you can understand that is the maximum voltage, but when we have the calculation of the V average, then we will get the VP output by pi. And how it is, you already did in your plus 2 level. I am not going in detail about the derivation of the same. It is, we have to consider the 1 by twice pi, 0 to 2 pi, then Vp into sine omega t dt. If we will do this integration, then the outcome will come Vp by pi. So this is the average voltage. Now the PIV is equal to peak inverse voltage, PRV is equal to peak reverse voltage. So maximum voltage which is across the diode in the reverse bias mode, that is basically the voltage, and that is called the peak reverse voltage, right? Now the average DC load current, the average or DC value of alternating current is obtained, I already told you that, obtained by the integration. So for finding out what we have to consider, this is the mathematical relation. I think you are already familiar from the plus 2 level. Then IL is equal to Im into sine omega t, right? When 0 means in the first half cycle, but we know that in the negative half cycle there is no current flow, right? So at that time IL is equal to 0, and that's why it is called the, only we have to consider 0 to pi, that means in one half cycle, right? And if I'll do this, then we will get the average DC load current. This is the formula I already told you, and if we will do it, then this is the formula Im by pi or Vm by pi. So the derivation I am just showing here for your reference. You already did this in your plus 2 level. Okay, so this is the, as no current flows, so this is the formula, and after the derivation we will get the average value, and this average value corresponds to the direct current when we will transfer through the after the applying the half wave rectification, we will get the outcome as Im by pi, right? So this is the waveform, the practical waveform, and this is the output waveform. This is the looking like this because there is one half cycle only present, and in the negative half cycle is not showing here because of the half wave rectifier. Now what we will do a very simple calculation. There the root mean square, the root means squaring, finding mean, and then finding the square root. How we can do these things? IRMS. For IRMS it is a very simple calculations. We know that root mean square is basically 1 by, first we have to do the square, then after that we have to do the mean, and then again we have to do the root. So this is the way we have to do, and this is a simple calculation where the IRMS is equal to Im by 2. The RMS value is also very important parameter in case of half wave rectifier, because when we will do the parameter calculation for half wave as well as the full wave, these values are very crucial, right? So average load current, already I discussed about this, and the peak inverse is basically the peak inverse voltage. I already discussed in my previous slide. So this is okay. Now we will go for the efficiency of half wave rectifier. So eta is equal to output DC power by input AC power into 100%. Means we know that when we are when we want to find out the efficiency of any devices or components, then this is the standard formula. That means how much we are getting divided by how much we are given into 100. So the input AC power, that is we can do 1 by twice pi, 0 to 2 pi, instantaneous power. What is the instantaneous power? That is a product of voltage and current, and this is a simple equations. If we will do, there we can see that ID square, we can replace this ID, so 0 to 2 pi ID square d omega t. This is nothing but a IRMS. So IRMS we can put here, then Im by 4. So like this way we can get the PIAC and the output of the DC power. It is very easy because it is I squared DC. I squared DC is nothing but a I average. So we can replace this with I average value, and then we can get the rectifier efficiency. And what is the value? It is coming that 40.6 into RL by RF plus RL. What is RL? RL is the load resistance, RF is the diode resistance. So you can understand that diode resistance is very less. When it is equal to the load resistance, then the efficiency will drastically reduce, almost half. So we better to think about that the load resistance should be very high. So that's why we put the load resistance in the kilo ohm order, such that we can get the efficiency 40.6. But obviously the question will arise that the efficiency is very less. Yes, because we are only utilizing the positive half cycle of the system. Next, the ripple factor. So the ripple factor is a factor which is basically used for any components, the steel present, the achieved the unidirectional current, and for the filters we have to find out that what is the value of the ripple factor, and that we generally do the calculations, that means the noise, residual noise which is present in the output form, and that's why we are using the ratio I prime RMS divided by IDC. That means how much the residual noise, I mean the residual part is present, that we have to calculate. So this formula, instantaneous value of the ripple current, that we can find out ID minus IDC. So this is a simple mathematics. We have to do this simple mathematics, the integrations, and then we can find out the value of the ripple current. So this is a simple calculations. I think you people are smart enough to understand this. I don't want to do these calculations. You can do step by step, then you can get the results. Here the step by step calculations are shown. So this is the ripple factor. So ripple factor, that means the noise is very high, that is 1.21. What we observe. So up to this, the applications, what the applications of the half-wave rectifier, if you'll ask me, then the question is very valid. Generally we are using it in the where we need huge power generation for a very long time, for a very short time. There we can use this, like the firing circuits, also for the signal demodulation circuits, where the demodulations means that what is after the signal is reaching in the in the end where we should extract the signals, the voice, the picture, for these we are using this type of demodulation circuits. Also for the soldering iron circuits and also the amplitude modulation radio circuits as a detector, we can use the half-wave rectifier. So far what we have learned, that is the circuit diagram, input and output waveform. I showed you the average RMS peak inverse voltage, the knowledge of this, and lastly rectification, efficiency and the ripple factor. So these parameters we discussed for the half-wave rectifier. Now we can switch to the next part, that is a full-wave rectifier. That means a full-wave rectifier is very common to use in the circuits, because here we can use we can get the positive half cycle as well as the negative half cycle, and then the obviously the efficiency will increase because we can utilize the two parts, that means the positive and negative part of the alternating current. So what is the circuit diagram? Here you can see that is the input waveform, this input waveform which is the incident on the full wave rectifier, and after that what is the outcome? That is, you can see the negative half cycle is coming up. So we will get basically the full wave, the rectification, and here the two waves, the two part of the waves, that means in a wave, we know the crest and trough, this two crest and trough, this we can put it in one direction, right? So that is the utility of using the full wave rectifier. Next, the full wave rectification. Here the specialty is that we cannot use the ordinary transformer in case of the full wave rectification using the duo diode combination. So here we are using the two diodes only, right? And when we are using this, then we have to use a center tapped transformer. These are special kinds of transformer. That is the what is the special kinds, because the windings are different. In case of this, in the secondary coil there is a two types of windings are there. The windings are just opposite, such that we will get the different that means another output. And you can see the RL, the combinations of the circuits are very much important. Here the input from D1, when D1 is on, then this will active. When D2 will on, then this part is active. So ultimately D1 and D2 both are active in this case, and we will get always across the load resistance, always we will get the output. And so there is the output is desired output will be like this. So here the negative half cycle is basically inverted, and that's why it is coming up. So this is actually the things. And here if you see that when the positive half cycle is coming, that means this will conduct, this will non-conduct, and the current will flow in this direction. So the circuit is completed. Similarly, when we will come to the negative half cycle, if you come to the negative half cycle, you can see this is the negative half cycle, then the current will flow in the opposite directions, and ultimately the circuit is complete. So we will get the negative half cycle on the up. So the directions wise we will get the directions will not change, so here the directions will come up. So that is the utility of the full wave rectification. Next questions, the application of the full wave rectification is basically that we will use in the adapter which we are using for the mobile charger, which we are using for the laptop charger, which we have used for SMPS switch mode power supply in the desktop computer. Also nowadays we know that LED TV television set is very common for us, and there also we have to use the DC current instead of the AC current. So from AC to DC we have to convert it, right? So the half wave, the gist that full wave, what is the VDC is equal to 2 Vm by pi. So 2 Vm by pi means it is almost double, right? So the number of positive alterations that make the full wave rectified voltage is twice that of the half wave voltage. How we can show it? That is V average is equal to 2 Vp by pi. Now the question is that why it is like so, because here when you did the previous calculation to find the what is the average value for a half wave rectifier, there we just consider one loop, that is 0 to pi, but we are not considering pi to 2 pi because there is no current flow through it. So in this case we are considering both. So here basically 2 into multiply by the 0 to pi. If we will do these calculations, then obviously we will get this value. So it is a 2 Vp by pi. In the RMS value for full wave, if we will do this calculation, then for the full wave we will get Vp by root 2. So these two values are given us to consider for the efficiency, to derive the efficiency and the ripple factor. So that will be the assignment for you. You can do in your home. The average value will be calculated. Follow the steps, which in case of half wave, and the efficiency is 81.2% and the ripple factor is full wave is a 0.482. What is from here what you can conclude, that the efficiency is increasing almost twice, and in case of the ripple factor, that means the noise is also reduced a lot from 1.21 to 0.482. So that is the advantage to use the full wave. That means we can utilize more part. Now here the problems, one of the problems, the exercises generally I am just given here for your understanding, that see that here the 100 volt we are applying as the input waveform 100 volt to the transformer. So when it will come to the transformer turns ratio from primary to secondary, it is 2:1. So ultimately it will half, so 50 volt will come here, but you can see from the figure that it is a center tap transformer. So if it is a center tap transformer, then what we have to do in this case, the RL is given here, so you can understand that center tap means when the positive half cycle, then this D1 is active, when the negative half cycle D2 is active. So ultimately across this V out terminal we will get always the pulses, that is both are in the same direction, positive pulses, right? But what is happening here, that the peak to peak is basically coming as a 25 volt, right? So 50 volt, so 2:1, and that's why we can get the from the reference to the peak is basically given 50 by 2. So that's why we are considering 2P, and that is the PIV, but the peak inverse voltage is always, the rating is 49.3. So here it is coming that what is the PIV, then you have to find like this 2 Vp, that means peak to peak voltage plus minus 0.7 volt. Minus 0.7 is basically the this is basically the diode current voltage. So you have to use this, and then we can get this. And what is the waveform? This is the waveform. So here this is the maximum, the peak to peak voltage is the 50 volt, right? So I think it is clear for you. And then the next question, which is very common question, a crystal diode having internal resistance RF is equal to 20 ohm is used for a half wave rectification. So here they are asking for IM, IDC, IRMS. I think it is very easy. You can also find out yourself. That is V is equal to 50 sin omega t, so maximum voltage Vm is equal to 50 volt. So if we use this, then Im is equal to 61 milliampere. IDC I think is a very easy sum, so you can do also. But the question is that what is the AC power input? AC power input, the important thing is that here when we consider the AC power input, then I square RMS into RA plus RL, so that is equal to 0.763 watt. Right, and the DC power output is basically 0.301 watt. So you can see that the energy is almost the outcome, the power in terms of the power, it is basically half, because we are using the half wave rectifier. One of the negative half cycle is basically missing, that's why we are not getting the output, proper output. What is the efficiency of the rectification? And here another thing is important. If you notice it carefully, then you can see when we are considering AC power input, at that time we are considering RA plus RL, as the diode resistance is also in the circuit. But when we are considering output, DC power output, at that time we are considering only RL, not RA plus RL. Why? Because RL is actually the load resistance. When we calculate the DC power output, at that time we will just across the RL, what is the potential drop. So based on these, we will consider this, and the value will come like this, 0.301. Similarly, DC output voltage, there also we are using the potential drop across RL, so that is the 15.52 volt. Okay, so I think it is clear for you that how we can do the calculation and what is the significance of the values, and whatever we are getting the efficiency that is related with the power, you can see that the efficiency is the same. If we will consider 0.763 and 0.301, then if we will do these things, we are getting the same kinds of the value, that is the ratio of these two, then we will get 40.6. So this is almost the same like what we got it. Right, now full wave rectification using the another circuits we can do, we can think about, that is the bridge wave, the bridge rectification circuit. For this is also given, the outcome will come in a full wave. But what is the importance to use this? There we don't need to use the center tapped base transformer, special kinds of transformer. We can use any general transformer, step down or step up, and then after that these combinations, you can see that the combinations are very much important, and you can understand that when D1, D2 is on, that means when the positive half cycle is coming, then D2 is on, and then through the RL, and then D3 is on, and it will just complete the circuit through it. So D2 and D3 will active. And similarly, when the current will flow in the negative half cycle, that means the current will come through it, then D4 is on, and then it will across the RL, and then D1 is on, and then the circuit will complete. So when D2 is on, that means in the positive half cycle, at that time D2 and D3 is active, and similar things when the negative half cycle, at that time D4 and D1 is active, right? So I think it is clear for you that why the bridge rectifier, the 4 diodes we are using, because of we can use the any transformer. We don't need the step down transformer, that is the center tap transformer. So that's why we are concentrating on that. The similar representation we are showing here, and I think with the color image, color arrow, so the line will indicate that how the current is, what I told you, the same things, right? Now the exercise, assume that the total voltage across the high voltage secondary of a transformer used to supply a full wave rectifier is 3300 volts. Find the average load voltage. I think students, you can understand this process, that if I will just consider, first we have to see that whether it is full wave or half wave. Based on this, we have to think about that what will be the asking for, that is since the total secondary voltage is 300 volts, it is given 300 volts. So if it is a secondary voltage, means the output of the transformer is 300 volts, then each diode is supplied 1/2 of this value. So ultimately it is a full wave, means we are considering here the duodiode combinations. So the duodiode combinations means half. So that's why it is just 150 volts. Another thing is important, that the secondary voltage is an RMS value. The peak load voltage VP is equal to VRMS by root 2. So ultimately, because you know that it will increase, VRMS means it will increase. So ultimately, that what is the value which is applied here, that is a 212 volts. So that is the question which is asked for, and the answer is the average load voltage is 135 volts. So I think it is clear for you. Next, the turns ratio. The turns ratio is of a transformer used in the 12:1. So the primary is connected to the power main. So why we do the exercise, the problems, because these problems are basically related with our that current work, the practical work, right? So here we can see that primary voltage divided by secondary voltage into secondary voltage. So from there we can find out that what is the secondary voltage based on the turns ratio. So from here we can get the voltage, that is 18.33. After that we have to do the peak voltage. When we want to find out the peak voltage, then it should be multiplied by root 2. So because it is the RMS. So the DC output voltage, that is Vm by pi, we know the formula. Then from there also we can get the peak inverse voltage. So the peak inverse voltage is basically Vm is equal to root 2 into Bs, right? So that like this way we can do this, the problem solve. Next, the turn ratio of the transformer of the bridge rectifier is N1 is. If there is nothing, only full wave rectifier is saying, then you can consider the duodiode combinations. But if it is the bridge rectifier mentioned, then you have to use the bridge rectifier. So then this is the problems. A similar way you can try yourself. Otherwise, after that maybe you can go for the hint. Okay. So next, in a center tap full wave rectifier, the load resistance is this, and then find the peak value, the DC. Or I think this question is not very problem making any harder things. So this is the answer. You can try yourself, and if it will not come, then you can think about this formula which you need to use in this system, right? So this is things. Now next is that the bridge rectifier shown in the below circuit uses silicon diodes. So silicon diode, if it says the silicon diode, then the cut-in voltage is 0.7 volt, right? Always keep in mind. So here D2, D3, D1, D2, the schematic is given. So what you have to find out, DC output voltage. So the DC output voltage and the DC output current you have to find out. So here the peak voltage is basically, that always you have to, when you are using the transformer, that is then you have to do this root 2, and if it is the center tap transformer, then by root 2, right? So the peak output voltage is basically this 2 into 0.7, because when why it is 2 into, because when one diode D3 and D1 both are active, and in the negative half cycle, that means in the next half cycle, the D2 and D4 both are active. So that's why you have to understand that when the D4 is active, then the D2 is active. So that's why 2 into 0.7 you have to subtract it. So average output voltage is V average is equal to 2V into, I think this is easy. So you can also find out this part. So next question, this is the last discussion problems. The power supply delivers 10 volt DC with a ripple as this, which is the better power supply. So you have to make a comparison between the two, the power supply A and B, and which one is given you the more outcome, that you have to find out. So what is the way of doing these things? The lower the ripple factor of a power supply, then the efficiency and this noise is less, means it is a better power supply, right? So for power supply A, we can find out the ripple factor. So the ripple factor, how we can do these things? VRMS. So the VRMS is equal to 0.5 volt, it is already given, and delivers 10 volt DC. So if 0.5 divided by 10, then we can get the ripple factor 5%. Similarly, in case of power supply B, what we can see that the V AC RMS is equal to 1 millivolt, that means 0.001 divided by 25. So from here we can get 0.004%. so that means power supply B is better because the ripple factor is less. So if the ripple factor is less, then the power supply is showing their betterness. Now this part is over, and now we are switching to the new part, the next part, that is the power supply. Design a power supply. There is two types of power supplies are there. One is unregulated, another is a regulated power supply. Regulated means I need 5 volt. Then in the output terminal always it will show the 5 volt, not more than this, not more than and less than this, right? So that is called the regulated power supply. So first we have to understand the unregulated power supply, and then we can go for the regulated power supply. Anyway, I am just starting with the applications. You know that in computer, the switch mode power supply, there we need the variable output, variable power supply. So 12 volt, 5 volt, 3.3 volt. So that's why it is called the SMPS, switch mode power supply. So there we can use that 120 volt or 220 volt AC is the output, the input to the power supply, and from there different variable power DC power supply power source will be dragged out from the same. So that is the advantage of using this type of things, that where we need not only one particular voltage. If you need 3 or more 4 particular fixed voltage, then we can use these circuits, right? So design a standard power supply. What is from AC to DC? You know that AC means power is coming to the transformer. Transformer is if it is a step down transformer, then it will reduce the power supply, and then after that we are using the rectifier. Rectifier is using the combinations of the diodes. You know that is one diode, we can use the 2 diodes, another we can use the 4 diodes. It depends upon the requirement of the circuits. Then after that we have some noise, that is in terms of ripple. We already noticed this part. So what we have to do there, we have to use some filter. So which the filter will do? Filter will basically reduce the noise, because it will eliminate the noise. So the eliminate the noise is a very ideal statement. So that's why we are saying it will reduce the noise. After that the noise, but some output will vary. So for that we are using the regulation circuit. So ultimately that is we can get the regulated DC output. So whatever I am saying that is written here. And transformer with trans ratio 20:1 convert the 220 volt 50 Hz input sine wave into a 10 volt sine wave. It can be possible, right? So from 220 to 10 we can get it. So the rectification of the circuit already we discussed in the previous part, and here you can see that the output is basically this is the waveform as output from the transformer. So this is the positive half cycle and negative half cycle after reduction of the voltage, and then the waveform as output after rectification. That means the positive half cycle will come up, and we will get that in the output part. So the rectification is completed. After that the output of the rectification will fit to the input of the filtration circuits. The filtration circuits are different combinations. Generally one capacitor can be ready to do these things. Again, we can use the pi filter, we can use the different kinds of filter circuits are there. So you can see here the input pulsating DC, that means 0, again it is coming to 0, from 1 to 0, again 0 to 1, like this way. So there we can use the charging and discharging of the capacitor. Based on this, what we can see that the points of the pulsating points, they are basically moving up, such that we can get a stable output, not like the pulsating. So that is called the filtration. Filtration means whatever the noise or the ripples are there, that should be eliminated from there. then it will be the ripple. The capacitor does the smoothing the pulses from the rectifier into more constant DC. So it is the what is the action, the function which I just discussed, that part is just written here. You can see that the same things which I just told you in the narrative, that part is given. So ultimately the ripple appears to be a sawtooth shaped kinds of sawtooth shaped of AC variation riding on the DC output, right? So now after that we need some regulation from unregulation, because this is not regulated. Suppose I need the 5 volt, then we can use the Jenner diode. This is a Jenner diode in the reverse bias mode. So here the output is a 5 volt. So if it will be more than 5 volt, then the voltage corresponding current will pass through it, and then the rest part you can see here. The rest part is basically showing here. So if the output varies for whatever reason, the regulator circuit automatically adjusts. That I told you that it should be regulates, means it will give you the fixed value. That is nowadays instead of Jenner diode we are using the power transistor 2N305555, means the last digit, 2 digits are basically significant to tell you that what will be the output of the circuit. Output means that how much voltage will be given, you can take as the output, right? So that is basically the regulated power supply. Nowadays the ICs or integrated circuits are already come up with the same story. That means the output and the input current will be the same. Now what we learned so far from this discussion, that is the difference between the peak average RMS value of voltage and current, both in case of half-wave rectifier, full-wave rectifier, as well as the bridge rectifier, right? Next, circuit design, construction of waveform, half-wave and full-wave. After that we did the derivation for the efficiency and the ripple factor calculation for both. After that the problems discussed related to half-wave and full-wave rectifier, and design the power supply. Last part is the design the power supply, unregulated to regulated, and discuss stepwise, right? So the students, if you have any questions, then no problem, you can feel free to ask me through my email. There is the email is given in there. So I think you are enjoying